So today we are going to do notes on Lewis structures. They can either be called Lewis structures or Lewis dot structures. And why we use them is because they are a way to model the bonds that are formed between atoms. So we're going to have two components of the Lewis structure. The first is the atomic symbol, which represents the nucleus and core electrons. And by core electrons, I mean any electron that's on the inner shell. So these are the electrons that are not involved in bonding. And because Lewis structures are showing us bonds, they don't really matter. Then we're going to use dots in order to represent our valence electrons. And our valence electrons, remember, are our outer shell electrons, and they're important because they're the ones involved in bonding. So if you need a review of what valence electrons look like, if you look at a periodic table, in order to determine the number of valence electrons, you just have to figure out what group it's in. So everything in group 1 is going to have 1 valence electron. Anything in group 2 is going to have 2 valence electrons. And then we don't look at our transition metals because it gets a little bit more complicated there. And then we pick back up on boron's group. It has 3, 4, 5, 6, 7, and 8 valence electrons. The exception here in our noble gases is that helium does not have 8. Helium kind of belongs over here because it has 2 valence electrons. But for helium, that's a full outer shell, which we'll get to in just a minute. So in order to do the notes today, it's a good idea to get out a periodic table. If you don't have one in front of you, then I recommend you get one. Or this one is from ptable.com. It's a good resource to use if you don't have one in front of you. So now let's get back to our notes. So what we're going to do is we are going to look at, on our periodic table, we're going to look at our second period. So we're going to be looking at these elements right here, and we're going to practice drawing Lewis structures just for those elements. So for lithium, we're going to do Li because that's the atomic symbol. And then we only want to use a dot that represents the valence electron. So because lithium is in our first period, lithium is then going to have 1 valence electron. And we show that 1 valence electron with just a simple dot. It doesn't matter if you put that dot on the top, on the left, on the right, below. I drew it on the right, doesn't matter. Okay, our next element in that period is beryllium with a symbol of Be. And because beryllium is an alkaline earth metal, it's going to have 2 valence electrons. Now, electrons do not like to be paired up until they have to be. So beryllium, I would draw as 2 separate dots. Now, on some places, you might see it written with the 2 dots together, and that's not wrong, but we're just going to always draw those 2 dots separately on different sides of the element. Okay, up next we have boron, symbol B, 3 valence electrons. So we're going to draw 3 dots around it. Once again, it doesn't matter which side you draw the dot, and it doesn't matter which one of the 4 sides doesn't have a dot. Next, we're going to draw carbon, which has 4 valence electrons. And then here's where it gets interesting. We have nitrogen, and it has 5. And once we draw the 4, now we have to go back and pair it up. And so we'll add a 5th dot. It doesn't matter which side you have the paired versus the non-paired on. Oxygen has 6. So we go 1, 2, 3, 4. Then the 5th and 6th have to be paired up. Then we have fluorine, symbol F, has 7. 1, 2, 3, 4, 5, 6, 7. And last but not least, we have our noble gas, neon. 1, 2, 3, 4, 5, 6, 7, 8. Now, if you look at neon, you might think, where do I even put a 9th one? And that's why a noble gas is considered a complete octet, because it already has a full outer shell. So let's read some information about Lewis dot structures. So although the octet rule and Lewis structures don't represent a complete picture of covalent bonding, they do help us explain the bonding scheme in many compounds. So some terms that I'm going to use throughout these notes are structural formulas. And the structural formula shows the arrangement of atoms and molecules and polyatomic ions. And in our structural formula, we're going to have pairs of dots. And these pairs of dots represent a shared pair of electrons. And instead of showing them as a pair of dots, I'm going to use a dash to represent my bond. Now, I use this term already. Octet is the general statement that says that atoms tend to gain, lose, or share electrons so that they then have 8 electrons in their outer shell. And this is a goal of most of the atoms on the periodic table. But there are some elements that violate this rule, and you'll want to remember these. Beryllium and boron, they violate this rule because they are okay being electron deficient. So they are okay having less than our 8 electrons. And also hydrogen, because hydrogen, if you think about hydrogen, it is in our first period on the periodic table. And so it has a full shell when it only has 2 electrons. And so hydrogen follows what's called the duet rule. Another term I'm going to use is lone pairs. And lone pairs are a pair of valence electrons that are not involved in bonding. So these are just going to be the electrons that fill out the octets of all of our atoms in the bond. So in a Lewis structure, a bond represents 2 electrons, and each dot is only going to represent 1 electron. So let's talk about the different types of bonds we're going to have. A single bond is a covalent bond in which one pair of electrons are shared between 2 atoms. An example of something that might form a single bond is the diatomic element chlorine. And if you think about why, chlorine is a halogen, and so chlorine has 7 valence electrons. And so what chlorine does is form a bond with itself and therefore just forms one single bond. Now here we can see that we have this dash, which represents a bond. And a bond, remember, is 2 electrons. And then this right here, this pair of electrons, that's not a bond. That is an example of a lone pair. So how we want to count electrons, and I'll highlight them as I count them, for each chlorine atom would be each chlorine atom has this bond, which represents 2 electrons. And then it has 1, 2, 3 lone pairs, which each represent 2 electrons. So when I count, I would count 2, 4, 6, 8 electrons on our first chlorine. And on our second chlorine, I would count 2, 4, 6, 8 electrons. So both of these chlorines have a full octet now with 8 electrons in its outer shell. Okay, let's take a look at things that might form multiple bonds. So something that forms a multiple bond is going to be when atoms share more than one pair of an electron. So an example would be oxygen. And in oxygen, if you remember, it has 6 valence electrons each. And so we can see the first bond right there. And then these electrons would also form a bond. But that's not really how we would draw a double bond. We would want to redraw this with the double bond between our two atoms and then our lone pairs outside. But if you look at why it does this, if I erase the second bond that I drew, without that second bond, each oxygen only has 2, 4, 6, 7 valence electrons. And when we have a double bond here in our second example, we have 2, 4 electrons in that double bond, and then 6, 8. And then the other oxygen has 2, 4, 6, 8. And so that's why oxygen would form here what's called a double bond. As you can see, carbon, nitrogen, and oxygen often form double bonds in order to make a full octet. And then another type of multiple bond is a triple bond. And something that would do that would be nitrogen, because nitrogen has 5 valence electrons. And so hopefully you can kind of start to see here is our first bond. But then if you count for this, it would then only have 2, 4, 5, 6. Therefore, we need to add another bond. And now if I count again, it has 2, 4, 6, 7. So we would still need to form one more bond so that we could then have 2, 4, 6, 8 electrons for both of our nitrogens. So we would want to redraw this with our triple bond in between our two nitrogen atoms. And we can't forget our lone pairs on the nitrogen. Otherwise, it wouldn't have that full octet. So here we can see that we have in the bond 2, 4, 6 electrons in our triple bond, and then 2 as a lone pair. So this is called a triple bond. And things that can form triple bonds are nitrogen and carbon. So something to remember, a single bond is 2 electrons. A double bond is 4 electrons. And a triple bond is 6 electrons. So now let's try drawing some Lewis structures for ourselves. So the first thing that we want to do is we want to add up all of our valence electrons from all our atoms involved. Then we want to draw a bare bones structure using only single bonds. And we're going to put an atom in the center that's often written first in the molecular formula. And we're going to then complete octets on atoms that are bonded to the central atom. And then if there are not enough electrons to give the central atom an octet, that's when we're going to try some multiple bonds. So let's try. So once again, if you don't have a periodic table out, now would be a good time to get one out. So here in our first thing, we have nitrogen trifluoride. So nitrogen has 5 valence electrons, and fluorine has 7. But we have 3 fluorine atoms. So we would take that 7 and multiply times 3. 7 times 3 is 21. So from nitrogen, we're getting 5. From fluorine, we're getting 21. So we have a total of 26 electrons to work with. So because the N is written first, that's a good indicator that nitrogen's in the middle, and it's going to be surrounded by fluorines. And we start by just drawing a dash in between them, which would represent a single bond. Now, those bonds used some electrons. So remember, each bond is 2 electrons. So our 3 bonds used 6 electrons. So right now we have 20 electrons left. And now is when I like to pause and see, well, how many electrons would I need in order to complete my octet? So nitrogen has 2, 4, 6 atoms, or sorry, 2, 4, 6 electrons around it already through the bonds. So it only needs 2 more. Each of my fluorines only has 2 electrons from the bond. So each of my fluorines still needs 2, 4, 6 electrons more. So nitrogen needs 2, fluorine needs 4, 6, 8, 10, 12, 14, 16, 18, 20. So I still need 20 electrons. And if I look, I have 20 electrons left that I can use. So in this one, this last step, if there aren't enough electrons to give an octet, try double and triple, we don't need to do because I only need 20 electrons to complete my octets. And I have 20 left, so I can go in and fill those in and not need to add any double and triple bonds. So what I want to do at the end is just make sure I didn't use too many electrons and everything has an octet. So nitrogen has 2, 4, 6, 8, and each fluorine has 2, 4, 6, 8. So everything has an octet. So now I just want to go through and count and make sure that I didn't use more electrons than I'm allowed, which is 26. So let's go through and count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And that was how many I was allowed. So this is a well done Lewis structure. Okay, let's try drawing the Lewis structure for water. So for water, hydrogen has 1 valence electron. However, we have 2 hydrogens, so that would give me 2. Oxygen has 6 valence electrons, so I then have 2 plus 6, which is a total of 8 electrons to work with. Now, in this case, hydrogen is written first, but nature really likes to be symmetrical. So I'm going to put oxygen in the middle with a hydrogen on each side. And remember, I start by just drawing a dash representing a bond for each of these. So in drawing this bare bone structure, I made 2 bonds, which means I used 4 of my available electrons. So I have 4 electrons left. And if I look, I need for oxygen, I still need 4 more electrons. But fortunately, hydrogen, remember, follows the duet rule. And so hydrogen doesn't need any more electrons. So I only need 4 more, which I have. And so I can just go ahead and fill those in without using double and triple bonds. And this one is the Lewis structure for water. Double check that oxygen has 2, 4, 6, 8 for its octet. And hydrogen has its 2 for the duet rule. And I only use 2, 4, 6, 8 electrons. So this is a perfectly good Lewis structure. All right, let's try one a little bit more complicated, CH3I. So carbon has 4 valence electrons. Hydrogen has 1, but there's 3 of them. So that would give me a total of 3. And iodine is a halogen, so it has 7. So this would give me 14 total electrons to work with. So carbon's written first. I'm going to put it in the center. I'm going to surround it by 3 hydrogens. And then if I look, I can't put an iodine on any of my hydrogens because hydrogen only likes to form the one bond. So my iodine must just need to go on that other side of carbon. So in drawing my bare bones structure, I drew 4 bonds, which then used 8 electrons. So I have 6 electrons left. Now, if I look at carbon, carbon already has 1, 2, 3, 4 bonds, which gives it a full octet already. Hydrogen follows the duet rule, and it already has its 2 electrons in each of these cases. So the only thing that still needs electrons is my iodine, which needs 6 more, and I have 6 more left. So I can go ahead and just fill in those 6 and not need to add double and triple bonds. So we've done 3 examples now without double and triple bonds. Let's do some structures that are a little bit more complicated. So let's try C2H2. So carbon has 4 valence electrons, but we have 2 of them. So that gives us 8. And then hydrogen has 1, but there's 2 of them. So that gives us 2. So that gives us 10 electrons to work with. Now, carbon, when possible, always likes to be in the center. And then we'll just put a hydrogen on each side because nature likes to be symmetric when possible. And in drawing this bare bone structure, I used 1, 2, 3 bonds, which then would be 6 electrons. So that means I have 4 electrons left. And here I can see that's going to be an issue because both of my carbons still need 4 electrons themselves. So because I don't have enough electrons, what I'm going to do is I'm going to add a double bond. When drawing that double bond, I just used 2 more electrons. So I have 2 left. And now each carbon has 2, 4, 6 electrons. So each carbon still needs 2 more. So I still need 4 more electrons. So because I don't have 4 more electrons, I only have 2 more electrons, add a triple bond. And in doing that triple bond, I just used my last 2 electrons. So I don't have any left. So I better hope everything has an octet. And in my triple bond, that is 6 electrons. And then 2 here, so 8. So each of my carbons has 8 electrons, and my hydrogen's following the duet rule. So it is perfectly good. So this is something that's going to need a triple bond. All right, example 5. Here I have boron. Boron has 3 valence electrons. And then I have fluorine, which has 7 valence electrons, but I have 3 of them. So that's 21. So 3 plus 21, I have 24 electrons. Because boron is written first, I'm going to put it in the center, and I'm going to surround it by my 3 fluorine atoms. And in doing so, I use 6 electrons. So that means I have 18 electrons left. Let's look at how many I might need. So each of my fluorines has 1 bond and then needs 6 more. So 6 times 3, I need 18 for my fluorines. And it looks like boron has 2, 4, 6. And so you might think, boron needs 2 more valence electrons. However, if you remember from our notes up here, boron is an example of an element that is okay being electron deficient. So boron does not need 8. So boron is perfectly happy with its 6. So with my remaining 18, I can go ahead and fill in the lone pairs on my fluorines and have a valid Lewis structure because boron is electron deficient. Okay, last example. So I have HOCN. Hydrogen has 1 valence electron. Oxygen has 6. Carbon has 4. Nitrogen has 5. So 1 plus 6, 7, plus 4, 11, plus 5, 16 electrons to work with. Now this one is a little different than the ones we've done before because instead of something being in the center, it's going to be a chain. Now, how I know that is through experience, and it is okay if as drawing this, you put carbon in the center, you could make it work. But let's try it as a chain. So in drawing the chain, I drew 1, 2, 3 bonds. 3 bonds would use 6 electrons, so I have 10 electrons left. Now here, nothing is electron deficient except for hydrogen, which follows the duet rule. So oxygen has 2, 4 electrons so far. It still needs 2, 4 more. Same for carbon. And nitrogen, it only has 1 bond, so it still needs 2, 4, 6. So I still need 14 electrons. And because I only have 10, I'm going to need to add another bond. Now, let's try adding it where it's needed the most, which would be on our nitrogen. So now, in drawing that new bond, I used 2, so I have 8 electrons left, but I still need 2, 4, 6, 8, 10 electrons. So that means I need to do another bond. Now, you might think I could put it right here, and you wouldn't be wrong. However, oxygen usually likes to form 2 bonds, and nitrogen likes to form 3. So let's put our last bond there. And so now I have 6 electrons left, which if I add my 2, 4, now carbon doesn't need it anymore because it has 2, 4, 6, 8 in the bonds. And then add my last 2 on my nitrogen. Then I used the right number of electrons, 16, and everything has an octet. So once again, it doesn't matter if you would have drawn it with a double bond and a double bond, because you would have put a lone pair and 2 lone pairs here, and you would have used the same number of electrons and everything has an octet. That is okay, but this is actually a better answer due to something called formal charge, which we're not really going to worry about. But the one I circled in blue is the correct answer. So best of luck giving Lewis structures a try on your own. Thank you.